like to take this opportunity to now introduce Amy from Houston, and she's the CEO and co-founder of TechSpace over there. And Amy, you're on live. Thank you.
Oh, thank you. Yeah. Good morning. Good afternoon. I'm Amy Henry, and I am the co-founder and CEO of Unique Ventures, as well as I'm here on behalf of TIE Houston. We're a corporate sponsor of TIE. I'm also on the TIE Houston board and on behalf of our new organization, TIE Angels of Texas. So we're very excited to be able to present Dr. Benjamin Kaebe. And it's through our work at Unique Ventures globally with technologies, as well as our partnership with people like Energy Conference Network. I'm personally excited being from Houston. Space has always been a huge part of Houston, besides our medical center, as well as our energy industry. You know, we've got programs like pipes and pumps and rigs to rockets. And when I was talking to Dr. Kaebe, I was excited to that what he is working on was something more than just space exploration. So I think everyone will be excited to hear what's happening in Western Australia. And then I will pass the mic to him. Thank you very much for your time.
My name is Benjamin Kaebe, Dr. Kaebe, and I'm the Executive Director for Space Industries. We have heard quite a few things about energy already. I have a bit of a different spin, and I think for those who are more interested in like what space can do for the energy transition and also for ESG aspects on like globally, I think there might be a piece for everyone in this talk. First of all, before I start giving more like insight of what Space Industries is doing, most people from Houston might actually know that, but sort of the motivation for us to develop our technology is NASA Artemis, and just a very brief explanation about what's going on. So there's a global aspiration to bring back the next human on the moon, amongst that the first woman. From there, the aspiration is to build a permanent presence on the moon. Then additionally to that, or following up from that, is a mission called Gateway, which will install in like a space station orbiting the moon, and the whole goal is actually then to go from moon to Mars. Why that is, I will allude a bit later on. So what's going on the moon? So because of NASA Artemis, there will be more and more satellites in lunar orbit for exploration, for scientific reasons, for communications. Then, as I already said, a lunar base. So mainly the research here will be conducted to actually find out if people can survive on a celestial body other than Earth, also how to grow plants and so on. So that's more a scientific reason for that. And as I said, Gateway as well, which is similar to the ISS, just orbiting the moon, to also sort of present communication to the lunar base and to conduct research. And the whole point then is to launch rockets from the lunar surface to go further. So the whole reason for that is the so-called Tchaikovsky theorem, the rocket equation. So if you want to leave the Earth orbit, you always use 90% of your fuel. And that's why it is an aspiration to actually start from the moon, because you have to use way less fuel to go from there. However, that obviously begs the question, how do you get the fuel to the moon in the first place? To do that, and that is where Western Australia sort of starts to tie in. Western Australia has a very long experience in mining, resource exploration, resource prospecting, and because of the harsh environments and vast distances, also remote operations. And that's why kind of a rover is interesting to us in WA, and specifically for Space Industries to do the prospecting, and then also for the resource utilization. And these points are where we are focusing on. Space Industries is developing currently the Lunar Resource Extraction Vehicle. That's a lunar rover with the goal to extract water, and for several reasons from the lunar regolith. So we've developed a technology which can extract hydrogen and oxygen, or even water vapor from the regolith. And the reason why that is interesting is, first of all, there's a high risk to actually bring that from Earth to the moon, and also very expensive. There's in the moment no other vehicle able to do that. And then, which is now the interesting part, hydrogen and oxygen can be used as a combination for fuel. That's how most rockets are actually being launched. If you have hydrogen, everyone who's in the energy area is knowing that this is actually in the big talk in the moment as well. So on the moon, that would usually then also mean that you have energy storage in some form, which can then be used to actually run Gateway and also to run the permanent base. And obviously, water is important, oxygen is important. So obviously, it's very desirable to have that. In the moment, bringing water from Earth to Moon is about $30,000 per liter. And by 2030, because of the NASA Artemis mission, it is expected to reach 16,000 tons per year. Another interesting thing, and that's where we actually started with, is helium-3, which we also can extract in the same procedure from the regolith. And helium-3 is interesting for a number of reasons. If we are focusing more on the energy part, helium-3 is interesting for anerotronic fusion to actually get a fusion reaction, with more research obviously being done. But a part of that, it is also interesting for propulsion, medical imaging, and supercomputers, and even more for neutron detection. So since 9/11, USA has depleted the helium-3 storages at ports and airports to actually hinder elements to smuggle nuclear weapons into America or dirty bombs. And therefore, it is desirable to have helium-3 back on Earth. Helium-3 is extremely rare on Earth. In fact, helium is already rare, and helium-3 as a stable isotope makes only 0.0001% of the helium deposits we have on Earth. The reason for that is, first of all, where do we get helium-3 from? It is generated in the sun as a product of the sun's nuclear fusion, and then transported via solar winds through billions and billions of years already in the solar winds. But on Earth, we luckily have an atmosphere, and that prevents the helium-3 from actually reaching the surface. However, obviously the moon has no atmosphere, and that's why the helium-3 is penetrating the regolith up to a couple meters in depth. And therefore, that's sort of where we try to extract it from. To actually develop the LREF, this is a bit more of a technology roadmap. So the LREF is the Lunar Rover Extraction Vehicle on the far right here. We actually identified a number of spin-offs, which by themselves are commercializable. And these spin-offs are, to start with, in the moment, a 3D printer. So we are currently developing a 3D printer to print parts for the Lunar Rover, printing in PEEK. So PEEK is polyether ethacetane. And the 3D printer has a size of 2 by 3 meter footprint and 1.5 meter height. Then to actually transfer the liquids and the energy from the Lunar Rover, we are developing a transfer port and deployable structures, which also have spin-off applications on Earth. The method itself has a spin-off in the volcano processing, which is patent pending in the moment. We're collaborating with one of the largest mining company in the world in the moment to actually use the same method to extract minerals and metals from ore without exceeding any CO2 emissions. And then the rover will also be used initially as a demonstrator and also for applicable situations on Earth to extract water from soil. And that can then obviously be used for agriculture and also to enable drinking water in remote locations. Then to store the water, we need lunar storage and habitats, which we are also developing. And then all these will lead to the final space demonstration production for the Lunar Rover Extraction Vehicle. And if you have a closer look at the picture on the right, there's actually a dish on the rover that's not for communication. This is the so-called solar concentrator, also patent pending in the moment. The solar concentrator is a deployable structure. The Australian Defence is in the moment very interested in this technology, and we're in the final round for a grant application in the moment with them. The solar concentrator can store electric and thermal energy, and because of the deployable structure, so you can see here on the right, sort of it goes out opens like a flower. It is self-cleaning, which is important for remote locations, such in the Pilbara, that's the desert in WA in the far north, but also on the moon, because the moon dust is actually covering the surface, and therefore at some point wouldn't allow any reflection anymore. And so the interesting part of the solar reflector is that we are focusing the whole energy contents of the solar light, of the solar radiation. That means we have a photovoltaic cell at its focal point, generating electricity, and then store it chemically so that we can use the electricity. But also, and that is the important part, we are storing the thermal energy from the infrared and using the thermal energy directly in our processes. And we believe that this is also a good way sort of to change a bit the energy usage, and could be applicable on Earth as well. So instead of having the steps from solar to photovoltaic, electric, and then to chemical, back to electric, and then maybe heating even something. So heat is often a main use of our energy. We can use the heat directly for cooking or even for cooling. Conceptually, how the whole process would work, our lunar rover extraction vehicle will heat the lunar regolith. So we don't have to dig down any shafts or anything. So the rover is actually just driving on the regolith on the moon surface, deploying its structure to actually capture any of the emissions we want to capture here. And by heating up the lunar regolith, that's well known since the 90s, it is like about 300 degrees Celsius. It will then release the helium-3. This and also the water vapor will be processed in the stage 1 processing and then stored on board. The rover then would return to the lunar lander, where there's another processing unit which is separating the water vapor from the helium-3. The helium-3 itself is then loaded on the return vehicle and will then brought back to Earth, and this can become a cycle. And it might sound a bit sci-fi here at this point, but I just want to sort of remind that this has been done just this year as well from China. So we have actually done lots of missions already bringing samples back from the moon. It's just a matter of logistics, and SpaceX is also a very good example of how sort of a change on disruption in the logistics chain can actually change how things are done. So, but what is also important is the aspect of remote operations. Doing them well will obviously also lead to less energy consumption and more efficient use in remote locations. Here in Australia, the labor cost is very high, and the OHS regulations are also very strict. Therefore, putting people not in harm's way is very desirable. And on this graph, I want to show sort of the level of autonomy on a robot, for example. In our case, it will then finally become the lunar rover extraction vehicle. So we have certain levels of autonomy. It starts with a teleoperation and the autonomic operation. So teleoperation means somebody sits at a remote controller and lifts a button or something, and the asset is then moving directly. Obviously, if you do that on Earth, that might be feasible. But if you go further and further away, for example, the moon or even Mars, you get a long return trip time because of the speed of light. So therefore, at some point, you can't do that anymore. Automatic operation is then something you might have in a factory where obviously you know exactly what's going on and you can pre-program it. However, on other celestial bodies or in environments where we are actually not aware of everything, or where something can happen in between, you can't really predict everything. So therefore you go then to the semi-autonomous operation, which means to still have sort of control, but you give a command and that command gets executed. The robot can interfere by, for example, avoiding an obstacle, but otherwise it's doing it all the task itself. And for a fully autonomous operation, you sort of just give a mission and the robot is then deciding itself how to do that. Some examples in space, like in the 60s, we had the Moon and Mars exploration during the space race between Russia and the States. So the teleoperation has been done on the moon when people have been around there. So there was actually not a remote operation from teleoperation from Earth. And also the autonomic operations are, for example, dockings. Then on the International Space Station, the Canadarm, for example, is a very good example, gets teleoperated. But now with the Mars exploration, we have more and more atomic and semi-autonomous operations for actually the reasons I just explained. And in the future, for deep space exploration, it is more and more desired to get the fully autonomous operation. And then also, like in the maybe further down the line, and this is more where maybe a new industry can emerge once we have more and more standards for satellites, and such as the transfer port. On-orbit servicing gets like an opportunity, which can then sort of lead to a increased lifetime of satellites, and also repairing them, and also just cleaning up the orbit, and for surface exploration and so on. To build all this, and this is sort of the thing we are really focusing now on, we need a headquarter, and we need a space, pardon the pun, to actually build all this. And we believe that this shouldn't be done just by ourselves. So that's why we want to build the Western Australian Space Precinct. And this precinct is inviting startups, SMEs, and primes in the world to come to Perth into this precinct, and then having like sharing, for example, facilities so that overhead costs can become like more cheaper, and specifically to startups, they can use the infrastructure at this place. This precinct will be built directly here in Perth at the airport, which is interesting because Perth Airport is currently undergoing a change. So the west part of the airport is already a technology park, but also has certain locations for touristic attractions. And we want to add with the precinct another part of the puzzle, so to say. So the main building which we are building initially will be housing a space technology museum, but not only that, that is important because this will sort of guarantee our short-term revenue so that we can reinvest and attract more and more people. And the location is specifically for Australian like situation very well located, because you can reach it with a train station very conveniently. Which is not the case for most of the other locations we have in WA. But it will also house a mission control center. It will house a clean room in a size which is like not seen in the Southern Hemisphere, lunar simulation rooms, and AI and robotic rooms, and so on. And these rooms will also be part of the museum. So they will actually have a glass wall so that the visitors of the museum can see real space operations. And we want to sort of invite the public to see what's actually going on. We already are talking to partners and have selected a few. For example, we ourselves, we want to run the Space Tech Museum. So that will be under the banner of the WA Space Precinct and Space Industries. The Mission Control Center will be installed and run by and operated by Sabre Astronautics. And they are already running the Mission Control Center in Adelaide for the Australian Space Agency. And we have partnered up with them. So therefore, we have a real sort of operation already opportunity here. The server and systems, for them, we have partnered with AWS. Specifically, if you think of AI and robotics, it is, I think, a good idea to sort of work also in the cloud. Sabre Astronautics is doing that as well. Then for the rapid prototyping, we are talking to OLP Robotics, but also want to run that ourselves. The clean room in the Lunar Analog will be under our custody. And for the co-working office space, and where we also have engineering offices, providing, for example, also simulation and CAD tools and so on, so that again, startups will not have the overhead costs. That will be run by Core and SpaceTube. Might not tell too many people anything, but in Australia they are quite advanced, and they run like shared office facilities for startups. Obviously, we also have other partners who are already working with us. Just to show a few, but I don't want to sort of bore you with more detail here. And I want to thank you for the invitation and for the opportunity to present Space Industries.